Hi everyone. Got several different equations to solve with you today. We're going to solve some exponential equations and we're going to solve some logarithmic equations. So these are your two main types that we're going to look at, and I'll show you different strategies for solving these. And let's begin with some basic examples here. Solving exponential equations. The big idea is you have to get the exponential by itself. Once the exponential is by itself, you can inverse the exponential by doing the log on both sides, and then simplify and solve as you need to. For example, this equation is a multiplication of 2,000. Now that I'm not going to be able to undo multiply with log, but I can undo multiplication with division. So we're going to get 3 to the t power equals 225,000. Now I'm thinking about how we're going to get t by itself when t is unknown and stuck in the exponent. And that's where we've accomplished this step. So if we've isolated the exponential, then we can use a logarithm on both sides. So what I'm going to do is I'm going to put the log function on both sides. It's kind of like dividing on both sides. It's kind of like adding in both sides, but when we divide and add on both sides, this time we're putting a function on both sides. So this is like f inverse here. And I'm doing the inverse function on both sides, and I'm going to take the previous equation as my input. And so then log of 3 to the t power, we have a exponent command or exponent law that says, oh, we can simplify this as t times log of 3 equals log of 225,000. We are almost done. We can divide both sides by log of 3 and we have our solution. So there is our solution. T equals log of 225,000 divided by log of 3. And that gives us an exact solution. This is unlike the other method that we learned earlier in the chapter when we graphed. When we graphed the intersection, we were getting approximate solutions. Now, speaking of approximate, we've got the exact answer here, and maybe we need the approximate. So let's get the approximate solution. All right, you can see I put it in the calculator over here on the left, and I got about 11.21. Now, if we had doubts, one of the things that we could do is, oh, that should be, let's say 218. Let's say we had doubts. Did we do our algebra right? Well, we can plug in that solution and see if it checks. So we could come over here and put in 2,000 times 3 raised to the 11.218, and so you got to type it in right. I left off an 11 there. And we got just a little over 450,000. And because we plugged in a round off, we're not getting an exact result. But it's so close to 450 million that we know that it's checking. So we plugged in an approximation and we got an approximately correct answer here. That's one way to check. Another way to check is using the graphing method. But let's go on and solve another one here. And we've got an exponential base e this time. Now exponential base e cannot do anything to subtracting. If I want to get x by itself, I'm going to have to get rid of the 8. And I'm going to have to get rid of multiplying by 5. So multiplication, division, adding, subtracting, I can just cancel that or solve that with normal algebra. And I'm down to this expression here, 54 over 5. And I want to get the exponential by itself. Now it turns out you can use any log you want, and there's some strategies that might make it a little easier depending on what kind of calculator you have. But for simplicity, if we're going to reverse an exponential, I'm just going to focus on log base 10 and log base e, the natural log. And in this problem here, it's going to be the most natural to use the natural log because it's base e. I'm going to use natural log on this side and natural log on that side. And the natural log of exponential base e is going to cancel that one out. Now that's unlike the problem over here, because over here it was log base 10 and exponential base 3. So log base 10 and exponential base 3 can't really cancel it out. But we at least had that exponent law that allowed us to simplify the exponent. Here we can simplify a lot more because natural log and exponential base e are inverses of each other. So we're going to get 9x minus 8 equals ln of 54 fifths. I wrote it wrong on this one over here. I want to put 5. So we're almost there. We've got the x out of the exponent. We just have a little bit of cleaning up here to do to add on both sides, and we'll get 9x equals ln of 54 over 5 plus 8. And then lastly, I'm going to multiply by 1/9. And we could divide by 9 if you want, but I don't have very much room, so I'm going to squeeze it in this way. ln of 54 fifths plus 8. And that is our exact solution. And also, we could run that into the calculator and see if we've needed a round-off answer for some reason. But again, so a lot of times, the algebraic approach, we're going to want the exact solution, and that's it. Let's take a look at a couple more examples. Now, if you are using my notes, you have all 4 of these on one page like I do, but I don't have room to solve all 4 of these on one page. So I've devoted a separate screen to the B, C, and D. We'll see those individually in a minute. But let's start solving again. Now the game plan is to get the exponential by itself. Everything with exponential has to be removed. Okay, well that's easy to get started. Let's divide by 7. And once we've done that, we have 10 to the 3w equals, that is going to be, I'm spacing out here. Yeah, 49. Okay, so next I want to undo the exponential base 10. Well, I can do log on both sides. So I'm doing an equation, a new equation, and the new equation has got logs on both sides, and I'm taking the old equation as my input into the new equation. Now in this one, this is log base 10 and exponential base 10. Those two functions are perfect inverses of each other. So it's going to simplify to 3w. And we can divide by 3 on both sides, and we'll get an exact solution here, log of 49 over 3. Now, I just about wrote it incorrectly. It's like that would be wrong, because it's like 49 over 3 is inside of the log. But in this problem, only the 49 is input into the log. The 3 is dividing the whole thing. Sometimes it's safer to write it as a fraction to prevent any confusion where the 3 belongs. Okay, so I got an exact, this is exact answer here. And we could check that exact answer in the calculator. The first one I checked it by plugging in, but let's check this one by graphing. So I'm going to type in the original problem and do the left side and the right side, graph both sides, and find the intersection. So I'll get some of that set up here, and we'll see in a second what that looks like. All right, in my calculator on the left, you can see I've typed in the left side and the right side of that equation. And next we need to set up the window. As far as the x's go, I don't have too many clues on what x's to use. But one thing we could have done is actually gotten a decimal here. And if we'd gotten the decimal, we would have had a better sense of x. It's really small. It's about 0.5, so I don't need too much in the way of x's. And that's why I picked -3 to 3, just so I can kind of see what's going. Now on the y's, when I have y2 here, that's 343. So I'm going to have a horizontal line at that value. So it needs to be a little higher than 343. That's why I put 400. And then y1 equaling this side is going to be exponential, so that's going to grow. So I'm looking for those two to cross. So if we graph, let's see what it looks like here. And so there's the exponential, and it started really quick and just shot right up. Now I have an intersection. I'm going to go to the second trace button to open the calc command, go down to number 5. And we'll hit the first curve, the second curve, and our guess, and it's going to calculate, and there it is, 5.6, which is the same round off. I didn't give enough decimals here, but when I put this in the calculator, I get this decimal, and the graphing intersection also gives me this round off. So that's my confirmation that my exact solution is a good answer. All right, let's take a look at another example here. It's B on that same list. And so I'm going to solve this guy here and get x by itself. Similarly, I would divide by 81. And then I'm going to have 3 to the 4x equals 1/3. Now, in keeping with what I basically said, I'm going to use the log or the natural log on both sides. For those of you who are a little bit more sophisticated with the logs and have better understanding, there might be an easier log choice here, but I don't want to overcomplicate it by throwing a lot of options at you. So I'm going to stick with just doing natural log or log base 10. And I didn't really see a reason to do natural log because it's base 3. Nothing's going to happen good here with either one. So, but doing the log on exponential, I have the exponential log laws that allow me to simplify that expression. One more thing, I have another log law. Actually, it's an exponent law that allows me to simplify the right side. I'm going to write that as log of 3 to the negative 1 power, because that's what 1/3 is. And, hey wait, if I have a power inside on this exponential inside this log, I can use another log law there to simplify this guy. So I'm going to get 4x log of 3 equals negative log of 3. And if I want to get x by itself, I'm going to divide log of 3 on both sides. And this will simplify. These logs divide off. I get 4x. Hey, wait, what is log 3 divided by log 3? Well, that's going to be 1 times negative, which equals negative 1. And I'm almost done. I can divide by 4, and I get x equals negative 1/4. Now, this one we could check as well, but the numbers are kind of small that I think we could check it by just plugging it in. So if I plug in my answer, negative 1/4, I'm going to get 81 times 3. Now 4 times negative 1/4 is negative 1. And so that's 81 times 1/3, which equals 27. And that's exactly what it's supposed to equal. So now I've got confirmation that I do have the right solution here. All right, here we're looking at exponential base e. Now the natural log is great for exponential base e, but the natural log is not great for multiplying. So dividing is great for multiplying. I'm going to divide that on both sides. E to the 4t minus 1 equals 3/5. Now, since we've got the exponential base e isolated, I'm going to use the natural log. E to the 4t minus 1 and 3/5. And so I put the first equation and plugged it into the natural log equation. So I got natural log on both sides. Now the natural log and the exponential will cancel out. So we're simplifying quite a bit here. Equals ln of 3/5 plus 1, and then divide that by 4. So you can keep it that way, or maybe you want to make that division real clear by putting it off to the side. But now I have an exact value for t. And in the same way, I can check this solution. I can get a decimal approximation for that in my calculator, and then plug that approximation back into the original and see if it comes out approximately 3, or we could use the graphing method. All right, one more of these in this set. These are the basic exponential equations. And so let's get these guys solved. Here's one more example. There's another exponential base e. Natural log is great for that. But natural log can't really touch subtraction. Best way to deal with the subtraction is add the 40. So that's pretty standard with your typical algebra that you've been doing for years. And the same with multiplying 20. Logs aren't going to work too well with multiplying a number, but dividing does. It works great. All right, so I'm seeing another natural log. So I'm seeing an exponential base e. So let's do the natural log on both sides. Now, can I do this? No, that's pretty lame. It's like somebody who wants to write f of x, but they write it this way. That doesn't make sense. Natural log is a function, and the function has an input. So we need the natural log and the input here. So it's really bad grammar, and it shows kind of a confusion of what's happening here. When I'm doing this, I'm treating natural log like a variable, and it's not a variable. Natural log, actually, it's an inverse function. And so I want an inverse function notation. This doesn't make sense to write it that way. So when we're doing the natural log, let's make sure that we write it like it is. It's a function. It's like f of x. I have to put the f part first and then the x part next. So natural log, and then the input. Well, the input is 5. So the natural log of exponential base e, that's going to simplify down to 2x equals ln of 5. And then lastly, I can do 1/2 on both sides, and I've got x by itself, 1/2 ln of 5. And now that's also something we could check. Now I want to look at some exponentials that are a little bit more difficult.